Suppose that V and W are vector spaces. Then we can consider transformations from V to W. So that would be some kind of a process that takes elements of V as inputs and produces elements of W as outputs. And it'll frequently be helpful to depict a transformation as a diagram where the transformation is shown by an arrow. And then, just like we did with vectors in Rn, you can define what it means for a transformation to be linear. And in fact, the definition is exactly the same. A transformation from V to W is linear if T of U plus V is equal to T of U plus T of V for all vectors U and V in the vector space V, and T of K times V is equal to K times T of V for all vectors V and all scalars K. So again, the definition is exactly the same as it was before when we were dealing with transformations from Rn to Rm, but actually now that we're in this more general context of vector spaces, we can understand what the definition means a little bit better. The key point is that a linear transformation relates the addition and scalar multiplication in V to the addition and scalar multiplication in W. And you can see that in the equations because the plus signs are actually different plus signs. On the left side of the equation, the U and the V are vectors in V, and so when you add them together, you're using the addition rule in V. But on the right-hand side, you have T of U and T of V, which are vectors in W. And when you add those together, you use the addition rule for W. And it's the same thing with the second condition and scalar multiplication. So the idea is that a transformation is linear if you can do the operations, the addition and the scalar multiplication in V, and then transform into W, or you can transform into W and do the operations in W, and you get the same thing either way. All right, so let's look at some examples. As the first example, there's the thing that we've been studying all semester long, which is transformations from Rm to Rn. And we know that those transformations are exactly just multiplication by matrices. But what's really cool about this is that there are lots of other examples that you are very familiar with, and we can now just look at those examples and we can recognize them as being linear transformations. So for example, the derivative. So we can think of the derivative as a transformation on functions. The input is a function, and then when you take the derivative, you get another function as the output. So just to avoid technical issues about is it possible that you have a function where the derivative doesn't exist, I'm going to say that the transformation is from C infinity of R to C infinity of R, where C infinity of R is the space of quote-unquote nice functions where you can take derivatives as many times as you want and you never run into any trouble. This is really just a way of keeping things simple, and I'm totally okay with it if you ignore the details and you just think of it as something where the input is a function and the output is a function. But the important thing is what makes it linear. If t is the transformation that takes the derivative of a function, then t of f plus g is f plus g prime. But there's a property of derivatives that f plus g prime is f prime plus g prime. And it's because of that property that we see that t of f plus g is t of f plus t of g. And then again, there's a property of derivatives that you can pull constants out when you take the derivative. And that is exactly the property that tells you that t of k times f is k times t of f. So these properties of derivatives that you used all through your calculus classes are the properties that say that the derivative is a linear transformation. So here's another example that involves functions and calculus. If you have a function, then you can calculate the integral from a to b of that function, where a and b are some constants, and the result is a number. So that this definite integral is a transformation that takes functions as inputs and produces numbers as outputs. And the fact that this is a linear transformation comes from properties that you used throughout your calculus classes. The property that t of f plus g is equal to t of f plus t of g comes from this property of integrals that when you have an integral of a sum of two functions, you can split it up into a sum of two integrals. And similarly, the property that t of k times f is equal to k times t of f comes from the fact that you can pull constants out when you compute integrals. Those two properties are the properties that tell you that definite integrals are linear transformations. Another example that involves functions is multiplication. So you can take any function. In this example, I'm using x squared, and you can make a transformation where you multiply by that function. If you take a function and you multiply by x squared, then that's a new function. And so that is a perfectly well-defined transformation. And for this transformation, the property that t of f plus g is equal to t of f plus t of g is the distributivity law. And the property that t of kf is equal to k times t of f really comes from commutativity of multiplication, that x squared times k times f of x is equal to k times x squared times f of x. So in this case, it's really just simple properties of algebra that tell you that this transformation is a linear transformation. Yet another example of a linear transformation involving functions is the process of plugging in x values. So you could pick some particular x value a, and if you plug that a value into a function, then you'll get a number. And that is a linear transformation. And in this case, the property that t of f plus g is equal to t of f plus t of g really comes down to the way that f plus g is defined in the first place. That f plus g of a is f of a plus g of a. That's really how f plus g is defined. So the linearity of this operation is really built into the definition of addition of functions. And then similarly, for t of kf is equal to k times t of f, that really comes down to how k times f is defined. So I think it's worth pointing out that the examples that I've showed you so far are really like the basic building blocks of things that you can do to functions, right? You can plug in things into functions, you can multiply functions, you can take derivatives and integrals. There really aren't that many other things that you can do with functions. And so what's kind of cool is that those really are the basic building blocks, and then using those, you can produce other linear transformations by combining them together in different ways. So one way that you can combine them is by adding. As long as the outputs have the same type of vector, then you can add them together and you'll get other linear transformations. You can compose things. Remember that the composition of linear transformations is another linear transformation. So that's another way to combine things together. And then there's another thing, which I'm calling stacking, which you haven't seen yet, but when you see it, it'll be pretty straightforward. So just wait a second and you'll see an example. And so here's an example that incorporates all of these components simultaneously. It's a transformation that takes functions as input and produces vectors in R3 as output. And if you look at the components of this vector, each component is built out of the examples that we talked about earlier. So the first component is a second derivative. So that involves taking the derivative twice, which is a composition, and then plugging in 3 for x. And then the second component is 2 times f of 1 plus 5 times f prime of 1. So f of 1 involves plugging in, f prime of 1 involves taking a derivative and then plugging in, and then we're taking a linear combination of those two things. So it's 2 times f of 1 plus 5 times f prime of 1. And then the third component is an integral from 0 to 3 of f of x dx. And so what we've done here is we've taken 3 different things which would be transformations to R, and we've stacked them on top of each other to get a transformation that goes to R3, where the output is a 3-dimensional vector. And so that's what I mean by stacking. You take 3 things where the outputs are numbers, and you stack them on top of each other to get a 3-dimensional vector.
That's stacking! Stacking!
And then, as a final example, let's look at the transformation from R to R+, where R+ is the weird vector space where addition is actually multiplication. And we can define this transformation by the formula that t of x is equal to 2 to the x. To show that this is linear, we'll look at what happens when you compute t of x plus y. So that's 2 to the x plus y, and then using the exponential rules, you see that that's 2 to the x times 2 to the y. But now we're in the vector space where we're treating multiplication as if it's addition. And if it helps, you could rewrite that multiplication using the weird addition sign. And now you can see that the result is t of x plus t of y, where you're using the weird addition. And then similarly, t of kx is 2 to the kx, and you can use the exponent rules on that to rewrite it as 2 to the x to the k. And then remember that exponentiation is the thing that plays the role of scalar multiplication in this weird vector space. And so if you'd like, you can rewrite that using the notation for the weird scalar multiplication. And then we can see that the result is k times 2 to the k, where you're using the weird scalar multiplication operation. And so there you go. It's a linear transformation. And if you remember, when this weird operation stuff came up originally, we saw that this operation of taking 2 to the power of a number could translate between the ordinary operations and the weird operations. And now we're taking that idea and we're making that a little more precise by saying what we really meant when we said translation. What we meant was that taking 2 to the x gives you a linear transformation from r with the ordinary operations to r plus with the weird operations.